In this video, we're going to talk about how we can take derivatives of multivariate functions and what these derivatives are telling us. Specifically, we're going to be talking about what's called partial derivatives. So I have up on the screen the definition, the limit definition, I should say, of the partial derivatives of a function of x and y. So we are going to use the notation df dx, and it's kind of a fancy d, little curly d there. Df dx means the derivative of f with respect to x. And we can also note that as f sub x. So those notations mean the same thing. That would be the derivative of our function with respect to x. And then we can also take the derivative of this function with respect to y. We'll denote that f sub y or df dy. So the thing I want to point out with these limit definitions is that when you take the derivative with respect to x, we're taking the limit as h goes to 0 of f of x plus h, and then you have the y minus f of xy. So the thing that's changing in our limit definition there is the x's. So when we take the derivative with respect to x, we're figuring out what happens to this function, what happens to the z values when we change the x values. Whereas when we take the partial derivative with respect to y, we're now figuring out what happens to our outputs or our z values as we change the y values. Okay, so let's just first think about what this means graphically. So I have an example up on the screen. It says, given the level curves, determine whether each of these derivatives is positive or negative. So I've got a bunch of level curves and they're labeled. And I don't know if it's hard to read on here, but the first one is z equals 0, 1, 2, etc. Okay, so part A, let's figure out at the point 1, 1 is our f sub x, our derivative with respect to x, positive or negative. So first thing I'm going to do is I am going to find the point 1, 1, and that's right here. There's the point 1, 1. And then I'm going to look at what is happening to my z values as I increase my x values. How are the z values changing with respect to x? And so as I move along that arrow that I drew in the positive x direction, I can see that we started at, looks like a z value of 2, and then as the x's are getting bigger, the z values are actually going down to 1 and then 0. And since these z values are decreasing, that means our derivative with respect to x would be negative. A negative derivative tells us that the values are decreasing. All right, so what about our derivative with respect to y at that exact same point, at the point 1, 1? And feel free to pause the video and see if you can find the answer to this on your own. But this is how I would solve it. Now we want to know what is happening as we move in the y direction. And so I have kind of a lighter blue arrow moving in the positive y direction. And just reading the z values from the level curves, at that point, we're starting at z equals 2. And then as we move in the positive y direction, the z values are going to like 3, 4, etc. We're going uphill. The z values are increasing. And so our derivative would have to be positive. So another way of thinking about these partial derivatives is when you're taking the derivative with respect to x, you can imagine that you are walking in that x direction, and the derivative is telling you whether you're going to be walking uphill or downhill. And so based on this contour map, these level curves, we are going to be going downhill. But if we were to move in the y direction, we would be moving uphill our derivative is positive. All right, so how do we find these derivatives if we're given a function? Let's try to find f sub x and f sub y. So partial derivative with respect to x and y for the following function. So we've got the function f of xy equals y to the third plus 2xy plus y squared plus 4x. And so we're going to start with our f sub x. And we'll go one term at a time. And the basic idea is we treat x as a variable and everything else as a constant. So we're keeping everything constant except for the x's. So this first term, the y to the third, doesn't have any x's in it. So we're going to treat it as a constant. And the derivative of a constant is just 0. Then I move to my second term. The second term, 2xy squared, it does have an x in it. The x is being multiplied by a 2y squared. So this is kind of like a linear term. We have an x to the 1. The 2y squared is like the constant being multiplied by that x. And so the derivative of that term is just 2y squared. Okay, same reasoning as if you had like a 5x, your derivative would just be the 5. Okay. All right, so term number 3, the 4x, derivative of that would be 4. So my partial with respect to x is 2y squared plus 4. All right, let's find the derivative with respect to y. So once again, we'll do this one term at a time. So now we are treating y as the variable, and everything else, including the x's, we're going to pretend are constants, or treat as constants. So we're only thinking about what happens when we change the y's. So the first term, y to the third, that becomes a 3y squared. Second term, 2x times y squared. We're going to treat the 2x like a constant. So take the derivative of the y squared, bring the 2 down. We get 2x times 2y, or 4xy. And then finally, that last term, that 4x, doesn't have any y's in it. It's a constant. Its derivative would be 0. And so I'm going to write my final answer here as 3y squared plus 4xy. All right, let's do one more. We'll find our first partial derivatives for the function f of xy equals xy plus x squared, or over x squared plus 1. So I'm going to start with my partial with respect to x. So x is the variable. Treat y as a constant. And I'm going to use the quotient rule on this. And so I went ahead and said f is the top, the xy. G is the bottom, x squared plus 1. And so then the derivative of f, again, we're doing this with respect to x. So we've got this xy. Y is like the constant, so derivative is just y. So I labeled that f prime just because that's just how I have my quotient rule memorized, but technically we found the derivative of f with respect to x. And then if our g is x squared plus 1, our derivative of g with respect to x would be 2x. So now I'm going to go ahead and I'm going to plug that into my quotient rule. The quotient rule says if we have if we want to find the derivative of f divided by g, we're going to take f prime times g minus g prime times f all over g squared. And so I just went ahead and plugged the expressions above into that quotient rule. And then to finish, I'll distribute the y to the x squared plus 1. So that gave me x squared times y plus y. And then the 2x times xy is a 2x squared y. And then I'm just going to leave the bottom as x squared plus 1 squared. And then finally, if I combine like terms, 1x squared y minus 2x squared y is a negative x squared y. And then we still have that plus y all over denominator squared, or x squared plus 1 squared. So there's my partial derivative with respect to x, and I use the quotient rule. Now let's find our partial derivative with respect to y. And we definitely could use the quotient rule on this one again. However, I notice that there isn't a y in the bottom, only in the top. And in fact, I could think of this function as the expression x divided by x squared plus 1 times y. When we're taking the derivative with respect to y, this entire fraction, this x over x squared plus 1, we treat that like a constant times y to the 1. And so my derivative would just be x over x squared plus 1. Now you could use the quotient rule if you wanted to on this. Your f would still be xy, your g would be x squared plus 1. But then for the f prime and the g prime, we would take the derivative with respect to y. And so that would make your f prime just x, and your g prime would actually be 0 because there's no y's in the denominator. So plugging that into my quotient rule, I get x times x squared plus 1 and then minus 0 over that x squared plus 1 squared. And then I can cancel out my common factor of x squared plus 1. And that should give me the exact same answer. Now, we can also define higher order partial derivatives, so second, third derivatives, etc. And so up on the screen, I have the notation that we're going to use. So if we want to take the derivative of f with respect to x twice, we can write that as f sub xx, or the d squared f dx squared. If we want to take the derivative of f with respect to y twice, that would be f sub yy, or d squared f dy squared. All right, so those are two of our second order partial derivatives. The second two I have on the screen, this f sub xy, what that notation means, because the x is first, is it means you take the derivative with respect to x first, you get an answer, and then you take the derivative of that with respect to y. And we would write that as d squared f dy dx. And then for the last one, when you see the f sub yx, that means you take the derivative with respect to y first, and then find the derivative of that with respect to x. All right, so let's do some examples and see if we can come up with some generalizations about some of these higher order derivatives. So my next example says find all four, so all four of the things I had listed on the previous screen, all four of the second partial derivatives for the function f of xy equals 4x squared y minus e to the xy. So I have to find my first derivatives first. So I'm going to start by finding f sub x, my derivative with respect to x. So first term, I'm just looking at the x, I bring down the 2, and that's how I got the 8xy. Second term, e to the xy, I'm going to have to use the chain rule on that. So derivative of e to the xy, I just get an e to the xy. And then I'm going to multiply by the derivative of the inside. The inside is the xy. And let's see, we're finding the derivative with respect to x. So the derivative of x times y is just y. So there's my first order partial derivative with respect to x. So then I can take the derivative of that with respect to x again. That'll give me f sub xx, my second order partial derivative with respect to x. So I'm going to take a look at my answer, my f sub x, and I'm going to take the derivative of that with respect to x. So first term, 8xy, my derivative is just 8y. And then for the second term, we are going to use that chain rule again. So we have e to a power. So I'm going to get e to a power. And then we're taking the derivative with respect to x. So the derivative of xy is y. That's my chain rule. And then this other y just stays there. Again, we're taking the derivative with respect to x, and so that y that's outside of the e is kind of like a constant, so it's just staying there. We don't have to use the product rule because we're finding the derivative with respect to x. So if we go ahead and simplify this, that gives us 8y, and then I'll write that as minus y squared e to the xy. All right, so there is f sub x, x. Now I can also find f sub xy, and so now I'm going to take my f sub x, my first derivative, and I'm going to take the derivative of that with respect to y. So first term, 8xy, derivative is 8x. And then for the second term, though, this e to the xy times y, because we're finding the derivative with respect to y, we're going to have to actually use the product rule on that piece. So using my product rule, again, the derivative of a product, f times g, is f prime times g plus g prime times f. So I'm going to call f the e to the xy, g is just the y. And again, I'm taking the derivative with respect to y now. So the derivative of e to the xy is e to the xy, and then I have to use the chain rule, and that's why I'm going to multiply by that x. The derivative of x times y with respect to y is just x. The g is y. Derivative of g with respect to y is just 1. So plugging those things into my product rule, and then I'm also going to keep track of the fact that this term was negative. So I'm going to put my product rule in parentheses so I don't lose track of that negative there. All right, so f prime times g, so e to the xy times x times y, plus g prime times f, so 1 times e to the xy. And then I'm going to go ahead and just distribute that negative sign. And so there's my final answer, 8x minus xy e to the xy minus e to the xy. All right, halfway done. We got 2 more to do. So now I'm going to go back to the original function, and I'm going to find the derivative with respect to y, f sub y. So my derivative with respect to y, the first term, I'm just going to get a 4x squared. Second term, I use the chain rule, so it's going to be an e to the xy. And then derivative of xy is just x. All right, so there's my f sub y, and then I have 2 things to do. I'm going to find f sub yy. I'm going to take the derivative of that with respect to y. So 4x squared doesn't have any y's. Derivative of that is 0. Second term, we'll use the chain rule, so we're going to get a minus e to the xy. Derivative of xy is just y. And then I'm going to copy down that other x. Again, I'm not using the product rule this time, because the e to the xy is being multiplied by x, we're finding the derivative with respect to y. So we're treating that x like a constant. It just stays there. I'm going to rewrite this as negative x squared e to the xy, just because that looks a little bit nicer. All right, last one. Finally, I'm going to take the derivative of f sub y with respect to x. So first term, derivative of 4x squared is 8x. And then for the second term, well, I'm going to have to use the product rule on this because the e to the xy is being multiplied by an x, and that's what our variable is. We're taking the derivative with respect to x. So kind of similar to what I did before, I'm going to write out my product rule. I'll let f be e to the xy. My g is just that x. And then I'll find the derivative of both of those things with respect to x. So chain rule, the e to the xy becomes an e to the xy times y. Derivative of x is 1. And then I'm just going to go ahead and plug that into my product rule. But I'm also going to keep track of that negative, making sure I put my product rule in parentheses so I don't forget to apply that negative to everything. So let's see, we've got 8x minus the quantity e to the xy, y times x, plus 1 times e to the xy. And finally, I'll just go ahead and distribute the negative. So f sub yx is 8x minus xy, e to the xy, minus e to the xy. And so there we have it. We've listed all 4 of our second partial derivatives. And there is something that happened here if you look closely at your answers. The f sub xy and the f sub yx are identical. We got the exact same thing. And it turns out that is not a coincidence. That will always happen. The order that you take those partial derivatives in doesn't matter. Your f sub xy will always equal your f sub yx. And the same is going to be true with even higher order derivatives. So for example, if you compute f sub x y, so you take the derivative with respect to x twice, and then you take the derivative of that with respect to y, you could do this differentiation in a different order, as long as you have 2 x's and 1 y's. So maybe you take the derivative with respect to x, and then respect to y, and then respect to x. You'll get the exact same thing. So the order that you do that differentiation in doesn't matter with these higher order partial derivatives. So that's nice. Had we known that, we could have saved a little bit of time, and technically only had to find three different derivatives. These ideas of partial derivatives will extend to functions of any number of variables. I define them just for functions of 2 variables, but you could have a function of 3 variables or 4 variables. So I have, for my last example, a function of 3 variables. F is actually a function of x, y, and z. And I'm defining it to be 2z divided by x plus y. So in this particular case, we could actually find the partial derivative with respect to x, with respect to y, or we could even find it with respect to z. And so you can find a partial derivative with respect to any one of the input variables in that function. In this problem, however, they want us to find f sub x, f sub y, f sub x, y, y. So we'll do one at a time. I'm going to start with the f sub x. And I think I'd rather not use the quotient rule. And since x is only in the denominator and not also in the numerator, I don't actually have to use the quotient rule. Instead, I'm going to rewrite this function as 2z times x plus y to the negative 1. And then I'm going to go ahead and use my chain rule. Oops. So I brought down the negative 1. That gave me negative 2z x plus y to the negative 2. And then using the chain rule, derivative of the inside is just going to be 1. I guess 1 plus 0, or just 1. And then I'll rewrite that as negative 2z over x plus y squared. My partial derivative with respect to y, I'm going to do in a very similar way. So I'm looking at my function 2z x plus y to the negative 1. Y is my only variable. That's the only thing I'm worrying about. Treat everything else like a constant. So I brought the negative 1 down. Negative 2z x plus y to the negative 2. And then derivative of the inside is still 1. I guess 0 plus 1. So, oh, I actually get the same partial derivative. That is a coincidence. You can't expect that to happen. And then finally, third thing we're asked to find is f sub x, y, y. So that's actually a third order derivative. So that means, technically that means, we're going to take our f sub x, which we already found, and then we're going to find the derivative of that with respect to y. And then we'll take the derivative of that with respect to y again. So I've already found my f sub x. I have that circled in red. So then to find the derivative with respect to y, I'm going to use my chain rule again. So I brought down the negative 2. That's how I got a positive 4z. And then x plus y to the negative 3, chain rule, times 1. And then finally, the derivative with respect to y yet again. Bring the negative 3 down, so negative 12z, x plus y to the negative 4, and then again chain rule times 1. I'll write that as negative 12z over x plus y to the 4th. All right, that was my last example for this video. As always, let me know if anything is unclear.